Wasn't expecting this many people to turn out either. So, yes, a bigger room. We're fairly stuffed, so I'm going to start a couple of minutes early, because then I've got some chance of fitting in everything I want to cover. Because it's not really a 40-minute talk, it's really like a 70-minute talk. And I'm not good at judging that until after I've already written them. So, who here wants to learn some Go? Who here wants to learn some C? Who here never wants to learn any C? Leave. This is not a good talk if you don't want to learn some C. Mostly because I'm going to show off. Really, this talk is about comparing C and Go. But at the same time, it's about one of my favorite hobbies, which is tinkering in computers to make them think they're other computers. We're going to do just enough ANSI C for you to really be able to bend people's brains at some point. And we're going to do quite a bit of Go, because that's the point. But it might not be as much Go as C, unfortunately, until we get further on. Because I want to show off how to do stuff badly in C first. And this is all about machines. Now, I'm not good at dashing backwards and forwards. This bit here, unfortunately. So, we spend a lot of time as programmers having some bizarre imagining of what we think we're based mostly on blog posts, books on programming languages, and all kinds of other stuff. And what we think of ourselves as are special philosopher princes and wizards. Think insight into the world that other people don't have, which means we're about. In fact, in most ways, most adequately delusional. Keep reinventing Plato's cave and object-oriented programming is just that. It's like nothing more exciting than that. Unfortunately, machines.
Sorry.
Yeah.
You have to use these.
Oh.
Some problem.
That's okay. I much prefer these. Now I'm on. No? Yes? Hands up if you can hear me at the back, because now I sound very quiet. Okay. Machines aren't about philosophy. Well, I mean, there's a philosophy to the design of machines, but once you've built a machine, there's no philosophy involved. It's engineering, it's science, it's things that say yes or no, and you just can't change their mind without changing the machine itself. So this talk is a little bit about that. It's a little bit about learning to understand the kind of machines we deal with through building our own machines in machines. It's as simple as that. System virtualization is something that people talk about an awful lot, and my slide is now lacking, because I wrote this a couple of years ago. My slide is now lacking a very important picture at the bottom. It's got nothing related to Docker and Kubernetes. I may be the only person in the Go world who doesn't use either. System virtualization means different things to different people. To some people, it quite happily means running different operating systems in their boxes than the ones that were already there. To other people, it means containers. To some people, it means hardware emulation. To programming language designers, it means machine models. What does a machine look like? And up here, we've got a few popular ones. This over here is Microsoft's exciting infrastructure for .NET, which is probably a lot more complicated than that now. This is a very old diagram. Over here we have the JVM, which has cursed many a programmer's life, including mine. Down here we have that functional goodness that our friends in the Haskell world are always screaming is better than anything we do, implemented as an imperative machine under the hood, just in case anybody thinks functional programming has true magic. It doesn't. It's a great way to do design. It's an awful way to believe the machine will ever really work. Over here, we have possibly the two best ideas of how the machine really works. We have Forth, which looks an awful lot like machines actually do work. And then over here, we have C, which is missing some vital components that Forth lets you play with that machines actually have, and it abstracts them away for you. For our purposes, this is a machine. This is a computer.
They've all got pretty much the same stuff going on. We can sort of move these little lines on the diagram a bit. We've got a CPU that's got some local memory. We've got some remote memory somewhere that's a heap. We've got some kind of stack system so that we can push things on and pop them off, and that's how we do all of our call and execution frames. We've got some persistent storage that is so abysmally slow that even having a buffer that's a tenth the speed of the CPU is a 4 times speed, a 4 orders of 4 magnitude speed. So it's too early in the morning. And we have a network that used to be so damn slow compared to persistent storage that it was even more ludicrous to use it for storing data on. This is no longer quite true. I mean, I've got gigabit Ethernet, I've got AC wireless, I download games off Steam now, 3 times faster than the hard drive I owned 10 years ago was able to spin a platter. So these numbers aren't necessarily set in stone. But what we do have with both persistent storage and network, we have lag. We often have to send a signal quite a long way before we get an answer. So even though we'll get a stream of data fast, we talk to it quite slowly. That's everything we need to know. I'm not going to deal with persistent storage today because it's boring. I'm not going to deal with networks because I've got other talks on networks. I'm only going to talk about this chunk over here. Oops. I wonder why I've got that twice. Never edit your slides at 2 in the morning thinking that you're going to improve them. It won't work. So we're going to play around first with some stacks and some heaps to show you how those things are actually built in software. Then we're going to get on to the real meat of the talk, which is the bit that's absolutely scary to try and talk about, because some of it's very weird C and quite weird Go. And that's how we implement a machine that does stuff. And then we're going to show off some machines that do stuff and how those programs work that they execute. This is definitely not something to do before lunch. Possibly not something to do unaided by alcohol either. So the very first thing we have to think about, programs look like they're all about processing data, about doing stuff. But implicit in that is first, you have to have stuff to process, which means you have to have it stored somewhere. There's no point in having a brilliant CPU if you've nothing to put into it. It's the actual putting stuff in, changing it, and putting it back out that's the important part. So the first thing we have to think about is, well, we've got a chunk of memory. What the hell do we do with that memory? How do we make that memory useful for running a program? There's 2 basic, well-discussed methods of splitting up the memory in a computer. And there's a couple of others that actually never get talked about, but people do. So the first one is mathematician John von Neumann, back in the 1940s and the early 50s, came up with this idea of, well, we've just got a flat map of memory. Why don't we put a stack at the bottom that we pop things onto and pop things off? And why don't we have a heap down the other end, and we can store to an address and recall from the address? We won't let them meet, which is much easier today with virtual address spaces in the gigabytes and the terabytes of space than it was in the 1940s and 50s when you were lucky if you had a K of RAM. So, and a lot of our understanding of what to do inside machines often rests on John von Neumann's understanding in the 1940s and 50s, not on anything that we currently have as a modern processor. Now, the trouble with this one over here, with this von Neumann model, is we've also got to stick a program in this memory somewhere. And programs, by their very nature, involve things that say, please move to another location and do what's there. That's the whole point of a program. It has go-tos and executes. The John von Neumann model, unfortunately, tends to thread our data and our control signals all through the same place, meaning that if somebody can manipulate where the pointer for what we're looking at is, oh my God, they can turn data into executable code. Now, modern processors have all kinds of things like NX bits and all of this to stop that. But back in the day, and back in the day is not very long ago at all, as in there's still suffering buffer overruns today that will quite happily jump off and execute injected code, this stuff was considered a perfectly natural and normal way of doing things. People who work on embedded systems work in environments where they can't afford to let buffer overruns occur. And you can have complicated mechanics that allow you to check whether or not a particular memory location is tied to any particular use. And a branch of stuff in the 1960s called tag memory went down that route. And Burroughs made these really amazingly fast machines with very strange instruction sets. However, they weren't very easy to scale down into microprocessors, as in you just couldn't do it at all. So instead, another group of people came up with an idea called the Harvard memory model. This says, all right, it's okay if we have data and control in the same place. It's probably best if we don't have the code there as well, because then at least nobody can manipulate the code. Seems sensible. So you split memory up into these two chunks. You've still got control information over here on this stack, and that can still be used from time to time to skip around in a program in ways you wouldn't really want people to do. But now that takes a lot more insight on the part of a hacker doing that. So this isn't really a security talk. It's just this is the bit where security really matters. A chap called Chuck Moore in the 1960s, who doesn't seem to have been particularly concerned about any of that work, but was just trying to make radio telescopes work under computer control, came up with a language called Forth. And Forth is amazing because it's really little language. It's relatively easy to implement for a programming language, and it's relatively fast given its other constraints. And so he came up with this slightly different model where we now have two different stacks. One is control and one is data. We don't mind having code in the data stack because actually the code in the data stack is actually intended to be manipulated. That's one of the points of Forth. And then it is possible to then merge all of these things together into this kind of hybrid model where effectively we've got two different stacks going on. We've got two different memory spaces, so code and data never actually coexist. And then it's actually quite difficult for a hacker to basically break our program from the inside. That, however, is much more complicated hardware than that. And that's much more difficult for programmers to think about when they have to do clever things than that. Although Go tries to make you think more like the kind of programmers who live in that world. And half of my talks are about how to get around that. So stacks come in two basic varieties. There's the dull version that every single person who's ever implemented Forth does as a stack. I'm just going to kibosh a chunk of memory. I've got that chunk of memory. I've got a pointer into that chunk of memory. I will manipulate the pointer. That is my stack. I'll write to the top of the stack. They are brilliantly fast because you've pre-allocated memory. They also, unfortunately, are incredibly stateful. It's very easy to muck up the state of the stack. But they're very easy to implement. I've got an array. I have to do a malloc. This is all C, incidentally, for those who've never been scarred by an experience of C. I have to be able to push things on a stack, which means I've got to do a little bit more array manipulation. I've got to pop things off. And I've got a little program here, and all it does is it goes through. I push 1 and 3 onto the stack, add them together, print them out. I have the code in there, but I haven't really got time to show it. Which is a pity, because I wrote a whole pile of code that I didn't even find time to stick in the talk, unfortunately. It was much more fun than writing the talk, was writing the code. In Go, we can do pretty much the same thing. It's slightly easier for us in Go because we've got slices, so we don't have to actually do a malloc in quite the same way. And if we want to change the size of the stack as we go on, well, we can just leave the runtime to take care of that. And as long as we're not throttling over the edges of stack pages and stuff, it'll be fine. You know, saying, oh, I'll have a stack of, say, 2,048 integers is hardly a painful amount of memory burden in the modern world. Whereas John Voight Newman would have been like, oh my God, you mean you've built another great facility with a whole new set of computers in? I've got twice the RAM. You know, it's quite an odd sort of difference. We can actually simplify stack handling slightly in Go, because what we don't need is to actually implement push, because you'll notice push is only appending something onto a slice. And I can just do an append directly. So a stack in Go for a primitive array stack, not a lot of code. So the other kind of stacks, I've mislabeled this, and I've been meaning to change this slide for 2.5 years since I drew this picture. But I'm not really an artist, so that's it. It's not called a spaghetti stack. It's actually called a cactus stack. But I think they feel a bit more like a spaghetti stack when you get interesting with them. This is the basic data structure that lives inside all your functional programming languages. Singly linked lists. I spent best part of 30 years thinking, what a pointless thing. If I'm going back in a list, I want to be able to go forward in a list. And then I saw a talk by a friend of mine, Scott Volker, who also comes from an embedded engineering background. And he gave this talk at Strange Loop, which is North America's premier mind-bending functional programming conference for people who hate Scala. Which means 2/3 of the people there are actually Scala programmers complaining about Scala, which is really funny. But he gave this talk based on having forced himself to read through a book on functional data structures by a chap called Okabasi, I think his name is. And I watched this talk and I thought, I finally get the point. The point of a singly linked list is many of them can share the same antecedents. So now we can have portions of that list that are effectively immutable. Well, for a stack, this is lovely, because all I have to do is put things on the top of the stack, and the rest of it takes care of itself pretty much. I mean, I'm simplifying, possibly being slightly facetious, which is a bad thing to do in a talk. So, as far as possible, every one of these code examples on these slides is a fully intact program that you can just go take and run. That's why it's at 20 points. So I apologize for anybody short-sighted at the back who's squinting. So, this is how we would do a cactus stack in C. We've still got a push, we've still got a pop. We need to calculate depth for ourselves now, because depth isn't a number we want to carry around. We'd have to keep replicating it every single node as we went up, and that's just expensive. We also have to worry about garbage collection. So there's a garbage collector. There's not a lot to a garbage collector with singly linked lists. It's just, I've finished with that node now, I can get rid of it. That's one of the reasons the functional programming world really loves them, because garbage collection is an implicit part of their paradigm, and it works very lightly and easily. So this program here does exactly the same thing. I must be using sum somewhere, or I wouldn't have put it in there. But anyway, oh yeah, print sum creates a sum. So it prints out a set of sums. Unfortunately, these first two examples both come to the same number, 28, which was awfully bad slide design. And that shows that when you draw a diagram, you should actually read the numbers that come out of it before you decide to inflict it on an audience. So half of this talk is really about what not to do when writing slides. In Go, spaghetti stack, cactus stack is just as easy. I'm going to be obnoxious, and I'm not going to bother naming fields inside my data structures unless I really have to, because I'm kind of lazy like that, and Go just lets you. So why not? Also, it's slightly clearer intent to do something with an int than it is to do something with data, which doesn't really tell you a lot about what that kind of data is. But this is fairly simple. We have to create a stack. We have to be able to pop things onto a stack, which creates a new stack. And we need to be able to, or pop things off of a stack, rather. And we need to be able to calculate the depth. And it's not a very exciting example. It's there for completeness. Stacks are the easy bit. Heaps, not always so. So the point of a heap is, it's just a great big heap of things. I mean, I love the fact that early computer science just picked names that described how they felt about things. I've got a heap of data. I'll deal with it. So, unfortunately, I'm now going to teach you how to write map. Not map as in map a function, functional programming map reduce sense, but map, a data type, which we have in Go, but which we don't have in C. And so I've broken this down into 3 simple chunks. One is, we have a thing that we're actually going to call a map. That consists of an array of things tagged with labels. And it also sticks them into these buckets so that we can sort of spread them about so they don't all we don't want to end up with any one particular bucket too full, or looking for some things will take a lot longer than others. It's as simple as that. And I think it's the best thing I can say about that. We also need a search. Now, I spent about 3 weeks implementing this when I did it, looking at the code going, why can't I get these pointers to do the right thing? Because nobody ever writes maps this way in the literature. Oh no, they just basically go, I'm a C programmer, I know what I'm doing with indirect of double pointers. And I'm like, no, I'm not Well, I have been a C programmer. But I'm not anymore, and I'm recovering, and I don't want the pain of remembering. And it turns out nobody actually writes a search. Now, a search to me is fairly obvious. I mean, effectively, a map is just a database. So we have a search. We need to be able to step through to try and find something. We need to know what we're trying to find, so we've got a finder. And then we need to know if we are still searching or we found what we're looking for. And it's nothing more complex than that. And then we need an associative array. What's an associative array? Label, value, pointer. Label, value, pointer. Label, value, pointer. It's a really dumb singly linked list, effectively. We need to know whether or not we found the thing that's the right thing, and if it is, we want to get the value back, and if we don't find it, we want a null, because we're good C programmers, and we're going to pip a null all through our code. Honestly, I used to do embedded systems. You do not want to see the kind of code I used to write in C to go in hardware that was in planes. It was just like, I had nightmares for years after I left that industry. Had to be taken off a flight from Amsterdam because there was a bit of kit in the cockpit I'd written the certification documents for. Nothing's ever crashed that had that bit of kit in. It was perfectly safe. It's just I knew all the bits in there that should have still been fixed, that there was no way it was ever happening. And it's like, you work for Microsoft. I want to write one bug in 300 lines of code. Is perfectly OK for shrink-wrap software. I had to only have one bug per 3,000. That was quite bad. Quite a lot of my friends who were working on much more posh projects, things with missiles and stuff, 1 in 30,000 lines of code. OK, I get why Ada exists. That is the only reason. So our map acts pretty much the way we would expect a Go map to. We can stick things in, we can find things, we can change things. It's not a functional map, because it's mutable. So, and I don't really mean to rag on functional programmers. I actually have started doing quite a lot of my architecture using their principles. It's just they are quite holier than thou a lot of the time, and that gets to me. Now, an associative array isn't really difficult to write in Go either. So we're back in the world of Go now. And obviously, I'm going to short circuit this at the end of this section by showing you it would just be mapped. Because, I mean, we've got maps. Why the hell would we implement our own maps? Unless we maybe want to do something strange with how we store things relative to each other. Order-preserving maps, for example. We have to implement those ourselves. But we've got a find. We've got a getif. Our search is actually a little bit simpler, because now we're just stepping or searching. And I've got a memo up there, which means I can remember a place I've already gotten to. But I don't appear to be using it in this bit of code, which means it oh, I am, over here. So every time I go through in my Finder while I'm searching, I just make sure that I remember the last position, just in case. I can't remember why, but I think it was actually important to everything working. So, well, you don't want to move on. Right. And this is our map. Our map is just a slice of associative arrays that we just happen to have an algorithm that will decide which of those slice buckets to put stuff in, which means our map is growable, which is kind of fascinating. Oh, I'm going to have to speed up. So, and the two of them work identically. So, at the top is how we do it with Go, and normally, and the bottom is how our map does it. That's probably the only time anybody's ever going to show you how to implement map in Go. So, all right. Between our heap and our processing, though, we've got this other little thing. We have a cache, and that's because heaps are often quite expensive to go to. That associative array has got a lookup cost. It would be much easier if I could just have a local cache that I could go straight to. So, so now we're moving into my favorite territory, and the bit that normally gets me screamed at by other people in the Go community, the wonderful intersection of reflect and unsafe. For those who've never seen it, I have a project called Raw that allows you to rewrite memory on the fly. Just change the type of anything. For VMs, you actually need that at times. Try implementing forth without having both floating point numbers and integers in exactly the same memory location. Language spec doesn't ban it, so therefore sometimes people write programs where it makes sense to them. So, there are two things going on here. I've got a concept of serialization. That is, I've got a concept that I can grab a copy of something that's in memory and store it off. That's how I would stick something in a cache. I've also got this concept of being able to overwrite. And just for completeness, I've implemented bytes in case anybody wants to get at the raw memory themselves using something they wrote to handle, well, stuff in the bytes package. And then over here, I'm tampering with some memory. I'm overwriting that memory, and then I'm overwriting that memory again. And when the code runs, it shows some garbage. Because it actually looks like garbage. I mean, it's just basically a flat dump of numbers. So, oh, I don't really want to go into slice headers. I've got old slide decks. You can go and do horrible things with slice headers if you read them. The great thing about Go is most of the higher level types that we use on a daily basis, we can get at their lower level representations through reflect, do hideous things, and then use unsafe to write them back into memory. I didn't say that. This is what we really care about. We care about machines, so I'm going to speed really fast. Because this is the bit that I should go slow on. This very simple C program is a bog standard boring interpreter. Everybody who ever sits down to write a programming language implementation, the first thing they do is they write an interpreter, and they actually write a simpler one than this. They write one that actually uses strings instead of opcodes. This is a bytecode-based interpreter. So we've already optimized at least one step from a lot of basic implementations. And all we do is we run through the switch with a set of instructions, and we execute a program. In this case, we're adding 13 and 28 and getting 41. That's all of these examples are going to do. Right? We can slightly improve on that because using a switch is slow. So the next thing you do is you go, I don't want to use a switch, I'll use function pointers. I'll go directly to the function that implements that, and then the function will take care of doing all the stuff it needs to do, and then I'll remember to have some way of reading an opcode. Well, in this case, we're just incrementing through our program one step at a time. And that means that these functions, if they want to, can change where that PC pointer actually points to. Now, indirect threading, right, the first two examples, switches and direct threading, that's how everything used to be written. And then GCC introduced this idea that if there was a label in your local function, you could just grab the address of it, and you could use that as if it were a function pointer. And a few years back, CLang finally decided to add it as well. So now you can do this optimization on both. This is now a local jump, which is much quicker than a function call, because a function call creates a new stack frame and a few other bits. Whereas a local jump just goes, OK, I've just incremented a pointer or changed a pointer. Very quick. But the program itself, our program to use this, looks identical. Ooh. Now we can push this idea a bit further for readability. Go does not give us, unfortunately, a preprocessor. C does. This is why C gives us a preprocessor. Hardly anybody looking through code and seeing pointer PC post increment holds that in their head comfortably. But being able to write read opcode, you can hold that in your head comfortably. C can start to look like a fairly modern, reasonable language. However, notice, these look like they should be closures to us Go heads, but they are not. They're literally just text that's pasted into the code and it gets replaced. We should be approaching far too close to the deadline now. If anybody was planning on asking questions, I'm amenable to them over beer or wine later. So, now we can take this idea a step further. So we've got this list of local addresses, pointers that are actually inside our function. What if we could compile our program just to those jump addresses? Rather than having a set of function pointers that are globally understood, what if I could ask something to create me a list of label addresses that are only known inside the interpreter call? And I never planned to write a compiler when I wrote this set of code in the first place, but it just happened to fall out fairly easily, at which point I thought, why have I been ragging on C all these years? For this job, it's actually quite good. So compile and interpret have a fairly similar structure to them. Interpret knows how to do things, and as a result, I can put all of those pointer addresses in a dispatch table. And if I pass that dispatch table to something else, it can go through a program and do a copy of my program that's replaced every single opcode with one of the dispatch table addresses. And then I can return it and run it. So now I've got the ability to load an arbitrary program in, but have it in a compiled form that I could save if I wanted to. Might not be a good idea, but I could. And that then will automatically skip through all of these really, really fast, as if they're all local jumps. Boop. And then I can make it slightly more readable by using, yet again, C's wonderful preprocessor. Okay. We can do all these tricks we can do most of these tricks in Go. We cannot do the computed label trick. We just can't. We haven't got that. And that's really quite annoying. But we can do a switch interpreter, and the switch interpreter isn't very complicated. It looks like longer code because I've actually bothered to include the stack type in this one, which I didn't in this here. That's in an include file. It's actually a shorter portion of code to do the same job. And it's fairly readable. And we can do this direct call thing because we can treat function names as if they're actually pointers to those functions. And then we can ask up in the interpreter, we can skip our way through, and when we're running, we can force whatever we get out of our program to be a function call with no parameters, you'll notice. And then we can just call it. Boom, off we go. So direct threading is actually, direct caller based is quite easy. And we can do a few more things that are differently clever than C. We've got closures. So now if I want to, there's nothing to stop me from inlining function calls. And here I've decided to be boring and dull, and these aren't actually closures. They look like closures, but they take a parameter, and when they're called at runtime, the parameter is passed and it acts on the parameter. Now that would be quite good if I'm somewhere where I might have multiple Go routines doing the same thing or something in there. Because I'm always forgetting to put parameters on Go routine calls to stop myself from having stupid race conditions and ending up only doing the last thing in the program. But I can use genuine real closures over here. I can actually define, I've got an interpreter, and then when I create it, I can already reference back to the variable in it. So I've now got this, don't care what the function call is, don't need to have any parameters for it, which takes away a lot of complexity. Right. This here is a fairly generic virtual machine, and not a particularly nice one either, but it gets across the point. We can add that idea of compilation in. We can have a little assembler. In this case, I've decided to have a little assembler that it looks for labels, for named labels. So I can do jumps to a particular label. Hands up anybody who thought this morning they'd see how to write a compiler and assembler? And yet it's not a lot of code, is it? No. Don't be scared by systems programmers. They are mostly lying, and they are mostly blagging, and they are mostly winging it. The bigger the neck beard, the less they probably know more than you. So, and now I've got this nice little program. I mean, all of this, label, primitive, all of these are all things I've written in my program. I've written my program effectively as a Go program that runs as a program in this little virtual machine. All right? I've had to, unfortunately, introduce this concept of primitive, though, as a data type, because my program is now going to be, unfortunately, a slice of blank interface items, because that makes it easier for me to thread data in my program. And then I can let instructions take care of what the data should be. But this does mean, unfortunately, that I now have to actually specify that these functions, this is one thing I would love C to fix. I would like to just be able to put primitive and then the empty brackets and have it go, you know what, I'm quite good at spotting types in every other condition. This just looks like I'm using a type that happens to be a function. You know, but unfortunately, this is the one bit of the parser that drives me nuts because it adds verbosity I don't need. Now, processing units. I'm going to go really fast. I'm going to try and do one of these per minute or less. And then all the code is over, and then I'll show you the happy slide at the end that says, please go and look at this online, and then you can think about it for hours and days and weeks and months and years, and write me dirty letters if you don't like it. So this is a very simple VM harness based on the previous work. What this does is it creates the idea that we've got this little virtual machine that's got a program counter that knows where it is in the program. It's got some kind of memory that's some kind of slice of stuff and we don't care what. i.e. it's pretty much like a slice of an array of void pointers in C. And then we've got this idea of a map of labels to integers. That's basically just this label points to that address, right? And then we've got the little assembler, so we can automatically assemble, so we never have to worry about that in anything I'm going to show you. When we run, we just skip through executing primitives as we find them, and if we don't find one, we'll panic. And that's fine. We've got a genuine bug in our interpreter core, we should fix it. And then down here, we've got a simple bit for reading the program. All of that is taken for granted in every one of the examples that follows. So, stack machines. If you are writing a programming language, you basically can pretend that everything happens on a stack. Stacks are a bit slow because you have to load stuff onto the stack, you have to remember where the pointer on the stack is, you have to load it back off the stack, and you have to put answers back on the stack in the right order for somebody else to read them back off. But we can pretend everything is a stack. We don't have to care about detail. So in this example, we don't. We have our push for pushing something onto the stack machine. Under the hood, the stack itself has its own push, but we push onto the stack machine. We've got an add instruction that allows us to add two things together, and the result will be on top of the stack. It will eat two things off the stack, put one thing on the stack. And then we've got a jump if not zero that will quite happily go, oh, that's not zero, I'm going to jump to another location and eat something off the stack while it does it. Whew. And over here, we have a little program. This is a perfectly fully boring go-to-based stack machine. We've got a few little odd things going on, so we're using, obviously, instructions that come from the stack machine directly. We're also creating a little bit of a closure of our own so that we can directly access stuff in the stack machine, which is just to show you can be naughty. We're going to print out some state, which will just tell you the program counter and the data on top of the stack. And then we run and we use OS exit nicely to exit our program when we run it. That one is dull, because stacks are really easy to play with. Rather than a stack, where we have to keep doing these stack operations and shunting data on, and pulling it off, and shunting more on, and doing stuff, and all of this, and we're jumping all over the place, we can instead have something called an accumulator machine. This is a machine that has a single register. Everything we do happens on that register. We could still have a stack if we want, but we don't need it. All we need is to be able to access some memory somewhere to load stuff, and then we need to be able to store stuff back off. Now, all of these programs do the same thing. They count down from 13 to 0, and then exit. And until they get down to the 0, I mean, this over here, the jump if not 0, and the load value at the top, they define a for loop. Nothing more complex than that. Accumulator machines were very, very popular in the 1950s and 60s as toys. But they're not actually very useful because of the amount of memory accessing that you have to do to remote memory. So instead of going to the heap via a cache, you're going to the heap directly, and sometimes instead of going to the heap, you're actually going off to some kind of storage. So it's not so good. Register machines are what we mostly play with. Now, we've been told a lot of myths in recent years. Almost finished. We've been told a lot of myths in recent years about how our processes work. We tend to believe they have the instruction set that we as programmers see, sort of indirectly, murkily through somebody else's compiler. Most of them actually have a completely different instruction set on the inside. There's a totally different architecture. And many of them now have multiple co-processors inside that do different jobs for that processor. So, but we can abstract all of that as I can put some data in some locations that live inside my processor. And then I can manipulate that directly, and it might have knock-on effects. In this case, I need to be able to clear my registers, which means I just need to be able to create another slice of blank values. I need to be able to read value. Well, read value means I need to be able to actually read something from in the program. I need to be able to load a value from the program into a register, which I also need to be able to figure out at runtime now. And when I do an add, though, I suddenly get a speed up. It doesn't look like a speed up because I'm using a couple of temporary variables to hold some values. And that sort of isn't as much of a speed up as it would be in C. But I've got a speed up where I now do things directly between two registers. I no longer have to put them on the stack, take them off stack, put them off the stack, take them off stack. I only have to read some values out of the program in this case. And once I've set that up, if those values live in registers, I can do things much, much faster. I've still got my jump if not 0, only now it looks in the register to find out whether the value is 0 or not. So I can use any register I want to control my jump. And my program has mutated a little bit. I have to be able to load values, and more to the point, I can't just load 13 and it goes on a stack. I have to say which register it's going to go into. So register 0, 13, register 1, -1 for our decrement. But apart from that, it's a fairly non-exciting program. However, the great thing about register machines is that they start to show us there are other types of machines we can implement. It's all right, I'm not going to horrify you with code for this morning. I think I have got some examples showing at least a hypercube lurking in a very old version of this talk from like 2010 or something. A register can quite happily be any data type we want. And if we want that to be a hypercube, so that we've effectively got a whole network of things hooked with channels, and that just happens to look like a set of registers, we can do that. If we want it to be a graph, so basically, oh my God, I quite fancy implementing neural networks. Let's have a neural network machine. Fine, let's just have a set of registers that happen to be graphs, so I can deal with the portion of graph I want to deal with. Or if I want to do 3D graphics, fine. My registers can now be quaternions. I can do all that complicated 3D, bizarre, complex math stuff. Because we can abstract like that, it means the programs that we write as our bytecode suddenly become pretty much the same no matter what kind of architecture we want. I'm not going to go into that today, but there's fascinating talks on it. Anybody who wants to muck around with this stuff should go and see at least one good talk on Go and CGO. So I think this one is from about 3 years back. But I remember sitting there thinking, oh, some things I didn't know. It is possible to do assembly language with Go. I have never succeeded in it myself. I do not find the Plan 9 assembler that comes with Go particularly endearing. But that's a personal problem. Also, if you want to understand how to do performance optimization, which tends to be one of the things, the reason why you play with a VM in the first place is about, this talk is absolutely brilliant. It shows all the different ways of queuing, etc., and all the ways of doing performance optimization in terms of, if I remember rightly, little blue and red cars going down little roads in a very abstract sort of 3D graphicsy sort of way. And it's just, yeah, it's a talk I would have loved to have seen when I was sort of like 19 and 20 and first really getting into playing with these ideas. I have some code online. It's not up to date. The code that's in this talk will be joining the code that's already in there, because some of that code is quite radically different, because I might have accidentally rewritten a lot of it this week. These 5 books should be on your bookshelf if you want to understand what everybody who implements runtimes thinks about. This one down here, Threaded Interpretive Languages, that is basically every single variety of forth imaginable, how you would implement it. And it is one of the most difficult books to track down, because Byte Publishing, who used to have published Byte magazine, released it in like 1978. This one over here, unfortunately, the author died, and the author who was going to update it with a second edition decided to write a completely different book, which is nowhere near as useful. But this is the book that I actually learned how to write interpreters and language cores from, way back in 19... This up here is the standard text. It only has one chapter on the useful stuff, and it doesn't have code. That's the only book that really describes Java bytecode in any meaningful way that isn't sort of designed just for language writers. And this over here is just mad. It's well worth reading. You can find more on my SlideShare and my GitHub, especially how to do horrible things that break unsafe and reflect in ways that don't break the compiler. So thank you very much for your time. I'm sorry if that was a bit of a long random ramble.